Right, hello and welcome. This is the first instalment, well, it's actually about the 15th billion, but 56 now, doesn't matter. That does. But what we're going to do today, we're going to do about the first part of alternating currents, which introduces, well, the main part is generally stuff you might know from GCSE. Well, first bit is anyway about frequency and stuff, but we're going to go into root mean square value, explain what that means, and how to work out what's it called? Yeah, we know how to work out the root mean square value of current or potential difference. Sorry, I don't know why I thought resistance was there for a second. Mine went blank. Okay, so the first thing we're going to do is we're going to draw an AC current, well, on an oscilloscope, which we'll go into more in the next tutorial, but for now we're just going to draw a really bad one. Sorry, this is terrible, but you don't mind. If you get the idea, you know, that looks like a prison cell. Sack it. Just going to draw an alternating current. A little square thing. Imagine this is a screen, and you've got that, and it sort of goes up and down. So it looks a bit like a wave, really. It's not a really good one, but mind. Got a few dials, maybe on there, like an old TV. Right. I don't know if you can see that. Yeah, should be able to do it. Right. Well, that is a really bad drawing of an oscilloscope, but you can see we've got two values here. So I'll enlarge this bit here. It's crazy. So this is a screen, and you've got the line here, and you've got the peak and trough. So it's a bit like a wave, really. Is that the right way to draw it? Yeah, it is. Yeah. Just so, like you've got the amplitude of a transverse wave. What they call it in terms of the AC current is the peak. Actually, same sort of thing you could use it, but anyway, it's called the peak, the top bit, and the bottom bit, and the equal distance away from is like 0. There, so the equal distances away. So yeah, the frequency is a number of cycles that pass a given point every second. So a whole cycle is sort of like a wavelength, if you can imagine it like that. That's one cycle. So the time period for one cycle equals, I'll just put time p because I'm lazy, 1 over the frequency. So that is one formula. Probably you might remember that from GCSE. That's the formula we used. We did explain it in one of the chapter 5 videos, even though that was direct current. This is alternating current, which is slightly different. So the power supplied to a heater, for example, is still P equals I squared R. And if you don't know how we got that, you can look at one of the videos, many videos I've done on direct current unit 1. I think it was, let's see what it was called. Sorry, I'm just getting it now, so you can go back if you need to. Fairly sure it was EMF. Yeah, if you don't know where we got that, you can look back at the EMF video. I think about halfway through that, I do go through a formula near something like that. So again, that's where we got it from if you want to go back. But I'm going to assume you've watched that, or you know where we've got that formula from. So at the moment, that's sort of the main sort of peak of it. But we're going to do something called RMS now. So I'm going to move out of the way, give you a minute to pause it, and then we'll get ahead and rub it off. Right, hopefully you've paused it. It shouldn't take that long to pause it. Okay, so I'm going to get rid of all this, so I don't end up squashing root mean square value on, because because it is the most important thing out of all this you need to know. Right. So, what is the root mean square value? Well, before we can answer that, I'll just give you an introduction into what mean power is. Mean power. Oh, I put it up here actually. God's sake. Crud on the floor. And that is equal to half. So, yeah. So for your power, you've got P equals I squared R, yeah? So your mean power is going to be half of that. So that's at your peak sort of thing. Mean power is sort of your average, so it's in between the peak and the trough. So I'll draw this off. I'll rub this off, but you know, I'll explain sort of where we got these values from. So say at this point it should be equal distances away. That's P equals I squared R. This mean power is going to come somewhere halfway between that. I don't know if it works out, but so basically we're going to times this by a half. So half or 0.5, we're going to put times I squared times R. So that's the mean power of the alternating current. So yeah, so I'm just going to rub that off. So that's what I'm going to do, which is crazy time. Right, hopefully you've understood where we've got that from. Now we're going to go on to what actually the root mean square value is. So what is it? Well, the root mean square value, I'll write this out for you. The root mean, I'll just put RMS. Root mean square value of an alternating current, which is what we've been talking about, crazily enough, of an alternating current is the same value, is the value of the direct current so root mean square value of an alternating current, I just put AC above that, should be current there, but never mind, of an alternating current is the value of the direct current is it through the direct current is the value of the direct current that would give the same heating effect. It's confusing, this, the way it's worded would give the same heating effect. Same heating effect as a alternating current through the same resistor. Now I'm just going to write that out and leave it on the top. So that would give the same heating effect as value of the direct current that would give the same heating effect as an alternating current, I'll put AC, through the same resistor. Let me just finish writing that. So, the root mean square value of an alternating current is the value of the direct current that would give the same heating effect as an alternating current through the same resistor. Well, what does that? How can we simplify that a bit further for you? So, the root mean square value, which is, let me make sure I'm going right here. So just give us a sec. Yeah, so we're talking about alternating current here. So we're talking about the I. So the root mean square value of an alternating current is the same value of a direct current that would give the same heating effect as the alternating current through the same resistor. So we know that power is I squared R. So that means that, yeah, that's power. So that's like the energy transferred sort of power. So if you've got a resistor, for example, in a heater, your power is going to be the amount of heat sort of thing. Well, it's not the amount of heat, but it's the power sort of heat, if you can imagine it, that way that the heater gives out. So, I mean, that was just, we're not talking about general heaters here. I'm talking about anything, but I just use heaters as an example. So, how can we create some kind of equation from this fact? So, we know that the current of the root mean square value, so that's going to be IRMS, the current of the root mean square value. All it means of a direct current is the same value as a direct current would give. That would give the same heat effect as the alternating current in the same resistor. That is quite weirdly worded, even if you like to think of it that way. So we know the mean power of an alternating current is half of. Sorry about that. The power of a root mean square current, even. Sorry about that, I just thought I broke something. So the root mean square current, yeah. So the heating effect is the power, yeah. And we times by half because obviously alternating currents go one way and the other, and you sort of take an average sort of thing of one of the peaks. So that's why our mean power is that. So our mean power, because same heat effect or same power, is an AC current through the same resistor. So that now current through the resistors, that's AC. Sorry, yeah, that's DC. Because we were talking about DC before, and that's power of a DC current, and that's power of an AC current. So they give the same heating effect, so the same power. The mean power of an AC current is the same power as a direct current would give through that resistor. Hopefully it's starting to make a bit of sense because I've gone through it a few times. So a half, which is this one, times I squared times R equals I squared R. So we've done that. I'll just put these in brackets so you don't get confused. So the mean power, so they've both got power, yeah? You understand? They both got power, so they both produce power. They've both got a current, they're direct. So that's the direct, I just put that direct. C, and that's AC. So the direct C and AC current, when it's the root mean square value, or the mean power of an alternating current, sorry, that should be RMS. Yeah, so direct root mean square value of the direct current sort of thing. So the root mean square value is the direct current, which is that it is equal to the mean power of the alternating current because they give the same heating effect and power. It is a sort of heating effect. So the power of the AC current equals power of the DC current when it's the DC current is using the root mean square value of the current. So it is a bit confusing now, but I'm trying to explain it to you as well as I can. So how can we sort of simplify that? Because it looks a bit, there's a lot of square in there, there's got a half times, there's a root mean square value. How can we sort of make that a bit simpler? So the first thing we're going to do, what's it doing here? Yeah, we're going to divide both sides by R, because they're both times by R, so that gets us half times I squared equal I squared I of RMS squared. Sorry if this, yeah, should be 0. So when it says I0, it's just a peak current. No, it's just a current, it's peak current. Sorry, I should have mentioned that before. And obviously we can square root, because they're both square, so we square root both sides. I just put actually divide by r so you know how we've gone through each step. Square root. So if we square root I squared times a half, we get a half. 1 over root 2 times I equal I RMS. And then if we multiply out the left term, we get I, the current, over root 2 equals current of RMS. So that definitely looks a lot simpler than that, but they both, at the end of the day, mean exactly the same thing. So, and we can just replace, what do they do? Is that what they've done? Yeah, so we can just replace these with V. Yeah, so we can just do that. So I just need to plug in my camcorder. A minute. Sorry about that, I just did plug in my camcorder. Looked like it had enough of life on, to be honest. I wouldn't really blame it, but never mind. So I said we could just replace I with R with V. Hopefully that makes sense to you. It doesn't to me, but hopefully it does to you. So the root mean square value of a current or a PD is the V or the I, whichever one you're testing, over root 2. So that V is the peak value or the peak potential difference or the peak current. So that's just the peak. That should be V0. So that's the peak PD is equal over root 2 is equal to the current or the potential difference of the root mean squared. So just go over it again. Mean power of a current is of an AC is halfway between the peak and the sort of base 0 potential difference. And just because P is the I squared R of a direct current, that is, yeah, so you turn it by half to get halfway. That's why you've got I squared R in there. And now RMS is the of an alternating current is the same as value as a direct current through the same resistance and alternating current. So we make them equal each other. The direct current is now the root mean squared current, and then we simplify that down to get V or peak PD or peak current over root 2 with the corresponding either potential difference of root mean squared or the current root mean squared current. Hopefully that's a quick overview. If you're still not confident on that, just go over it again, watch it again, and we'll see you in the next video.